The biggest shift this week is that frontier AI is no longer just smarter. It's becoming more operational, more efficient, and harder to ignore from a safety standpoint. One result shows models successfully driving wet lab workflows end to end. Another shows you can reuse attention computation instead of recomputing it. And a third shows long context attention can be made much cheaper without losing quality. That means real capability is colliding with real deployment economics. Keep watching, because the details reveal where the next bottlenecks and risks actually are. Let's explore the first paper, ABC Bench and Agentic Biocapabilities Benchmark for Biosecurity. ABC Bench, from Secure Bio, is an agentic biosecurity benchmark that tests frontier AI models on 3 tool-using biology tasks: fragment design, screening evasion, and a liquid handling robot protocol for Gibson assembly on an OpenTrons OT2. The benchmark is built around a risk chain, from fragment design to synthesis screening evasion to wet lab execution, and it emphasizes objective scoring through automated checks plus real-world validation. In evaluation, the paper reports that all tested models outperformed the median human baseliner across the 3 tasks, with baseline human mean scores of 0.33 on fragment design, 0.22 on screening evasion, and 0.2 on liquid handling robot after 175 person-hours of expert baselining. Claude Sonnet 4.6 and Gemini 3.1 Pro Preview reached perfect liquid handling robot scores of 1, Claude Opus 4.6 achieved 1 on fragment design, and Gemini 3.1 Pro Preview reached 0.78 on screening evasion. The most striking safety-relevant result is that GPT-04 Mini high-generated OpenTron scripts that successfully performed DNA assembly in 3 independent wet lab experiments, confirmed by whole plasmid sequencing. The benchmark also exposes refusal behavior. On screening evasion, Claude Sonnet 4.6, Claude Opus 4.6, and GPT-4 refused all samples, showing that some frontier systems recognized the dual-use nature of the task, while still demonstrating strong biocapability on the other tasks. Let's explore the second paper, Can I Buy Your KV Cache? In Can I Buy Your KV Cache, Luo Yuanzhang of Harbin Institute of Technology, Shenzhen argues that a large language model's key value cache should be treated as a reusable commodity rather than recomputed for every reader. The paper shows that, for the safe shared prefix case, loading a pre-computed cache and continuing generation is token exact with from-scratch prefill under greedy decoding, matching 24 over 24 tokens and the logits, up to a maximum absolute difference of 0.02 on Qwen 3 4B. On Qwen 3 4B in FP16, the compute cost of reusing a resident cache is 950 times lower than re-prefilling, across context lengths from 255 to 3,774 tokens, with a speedup widening as length grows because attention cost scales superlinearly with sequence length. The measured break-even is essentially immediate, with NG in the range 1.02 1.13, so the second read already pays off. The paper also quantifies the economics of distribution. A 3774 token document produces a 557 megabytes KV artifact, and serving it to 80M agents would cost about $1. 5M if re-prefilled, about $0. 3M in reuse compute, or about $150,960 under a 0-1 pin cache read tariff. By contrast, shipping the raw FP16 artifact is unattractive because lossless egress is nearly incompressible and costs about $3 9M at commodity transfer prices. A simple int8 test halves a 102.1 megabytes artifact to 51.1 megabytes, but breaks exactness, confirming that lossless or selective compression is needed if reproducibility matters. The result is a concrete proposal for a provider-hosted prefill CDN that caches computation, not bytes, and lets agents buy access to a model-bound KV artifact instead of paying to recompute it. Let's explore the third paper, Minimax Sparse Attention. Minimax Sparse Attention, from Minimax with NVIDIA as a co-authoring affiliation, proposes a blockwise sparse attention layer built on grouped query attention that lets each GQA group independently select K key value blocks through a lightweight index branch, then applies exact softmax only inside those blocks in the main branch. The design is intentionally minimal. A KL alignment loss trains the indexer, while stop gradient, indexer warmup, and a forced local block stabilize sparse training. At inference, an XP-free top K kernel and a KV outer attention kernel turn sparsity into hardware speed. On a 109B parameter native multimodal MOE model trained on 3T tokens, MSA matches GQA quality while cutting per token attention compute by 28.4 times at 1M context. And with the co-designed kernel, it reaches 14.2 times prefill and 7.6 times decoding wall clock speedups on H800. The implementation uses BK equals 128 and K equals 16, so each query group attends to at most 2,048 tokens, yet retains strong long context behavior on ruler and helmet and stays broadly competitive on MMLU, GSM-8K, Human Evil, and multimodal benchmarks such as MMMU, ChartQA, and Video MME. That's a wrap on today's AI paper highlights. Thanks for watching.